Welcome to this module about Azure Stack HCI hardware requirements. My name is Manfred Helber. I'm a Microsoft Most Valuable Professional in the category Cloud and Data Center. In this module, you will learn the hardware requirements about Azure Stack HCI in detail. So before we begin with the hardware requirements, let's do a short recap of the HCI stack and infrastructure. As we learned in the previous module, we already know that Azure Stack HCI uses industry standard servers and combines this with a powerful software-defined stack for software-defined storage and software-defined networking. For sure, these industry standard servers have specific requirements regarding CPU, memory, OS drives, networking, and we will have a detailed look at these requirements to ensure that you know how to configure such a system. We will also talk about the certified solutions in the market, because via the certified solutions, it's easy for you to select an Azure Stack HCI compatible solution. So let's first have a look at servers, CPU, memory, and OS drives. So what are the requirements? Important is that all servers have the same manufacturer and model of Intel or AMD CPU. So you should not mix Intel and AMD, but you can decide for an Intel-based or an AMD-based solution. The CPUs you use require to support Hyper-V, because as we already learned, Hyper-V is our hypervisor we are using in Azure Stack HCI. It's important that each server needs minimum 32 gigabytes of memory. Usually, you will have more memory in your servers because you want to consolidate Hyper-V virtual machine workload, you want to consolidate virtual desktop workload and containers on these machines. And as more memory, as more CPU resources, as more storage power you have, you will be able to scale more up. But the minimum requirement is 32 gigabytes. For server operating system, VMs, and app workloads. Additionally, you will need 4 gigabytes of memory for each terabyte of cache drive. We will learn when we talk about the drives that the cache is optionally, but if we are running an Azure Stack HCI solution with cache drives, we need 4 gigabytes of memory for each terabyte of cache. Important is that we have a support for hardware virtualization. It has to be enabled in the BIOS or in the enhanced firmware interface. It's hardware asset virtualization. For the Intel CPUs, it's Intel VT or AMD V technology. We also need the hardware enforced data execution prevention feature. These are both features we can configure in the BIOS or in the firmware. We can use any boot device supported by Windows Server. It can be a RAID 1, it can be a mirror device, but it's not required to have redundancy for the operating system device, so it depends on your preference. We can start with 2 servers. If we want to build a stretch cluster, we need minimum 2 servers per site, so the minimum configuration is to have 4 servers in a stretch cluster. The sites can be in different countries, different cities, different floors, different rooms. It depends on your stretching scenario. So let's have a detailed look at the drives for Azure Stack HCI. We have 4 drive types we can use and that are supported for Azure Stack HCI. We can use the traditional hard disk drives. These magnetic drives always need some additional cache drives. Hard disk drives can be interesting if you need a huge amount of capacity with a moderate performance you want to boost via flash drives, for example with SSDs. Solid-state drives can be used as cache drives for hard disks, or solid-state drives can be used in a flash-only scenario. NVMe drives have the advantage that they are connected via PCI Express bus. So we have lower latency than with the solid-state drives, and typically we have a higher throughput than we have with the solid state drives, and typically also higher I/O rate. We can use NVMEs for cache for hard disks or for cache for SSDs, and we can use NVMe drives in NVMe flash-only scenarios. Persistent memory is the latest technology where we use memory modules with a persistent configuration as storage devices. This is the storage type with the lowest latency and the highest performance we already actually can get in the market. Persistent memory can be used as PMEM only configuration, can be used as a cache for NVMe or a cache for SSD. It's not possible to combine persistent memory with hard disk drives. On the capacity layer, we need minimum 4 drives. On the cache layer, if it's present, we need minimum 2 drives. The drive requirements are very flexible regarding the drive type. So we have a support for serial ATA, SAS, NVMe drives. We have different form factors for the NVMe drives that are supported. We have different hard disk emulations that are supported. Important is, for solid state drives and flash drives as a category, we need power loss protection. This is typically included in the enterprise grade drives. What's also important, we need the same number and type of drives in each server. So we will discuss this later in the drive symmetry considerations. So it's okay if maybe based on a replacement, we have a new drive in the server with a different size. Maybe it's a newer model, it's a larger model of an existing drive type. But what's not okay to have one server with SSDs and one server with NVMEs, for example. So the type, NVMe, SSD, hard disk, and the number of drives has to be identical in each server. Cache drives must be minimum 32 gigabytes. This is important because you could think about putting some very fast and expensive but very small drives as a cache in the servers, but they have to be minimum 32 gigabytes. Usually you have much more because usually you need 10% of your capacity as cache drive capacity if you want to configure cache drives. As I already mentioned, the cache drives are optional. So in a flash-only scenario, NVMe only or SSD only or persistent memory only, you can work without flash drives. The persistent memory devices, if you already worked with persistent memory, maybe you know this, there are different usage modes for persistent memory. And to use persistent memory for storage spaces direct in Azure Stack HCI, we need to configure them in the block storage mode. I already mentioned I can't combine cache drives with persistent memory and hard disks for capacity, but for sure we can use the persistent memory drives combined with NVMEs, for example. NVMe drivers are typically the NVMe Microsoft's inbox drivers. What's interesting, when it comes to an integrated solution, Microsoft will provide together with the OEM optimized drivers for your configuration. Number of capacity drives should be a whole multiple number of cache drives in the server. And the cache drives, this is very, very important, should have a high write endurance, at least 3 drive writes per day, because all the traffic will be routed through the cache. It depends on your specific configuration, if only for read or write traffic or for both. If you're using hard disk drives, then the cache will be used to combine writes and reads to the hard disks to optimize the throughput on the drives. If we are using NVMEs in combination for SSDs, for example, so 2 flash layers, we will not have the read traffic through the cache, but if we write data, it will be cached through the cache drives. For sure, here it's important to have a high endurance to ensure that your cache drives will not fail too early based on the workload you will have on these drives. It's also very important to know that the drives have to be connected directly to the server. Usually, if you are thinking about traditional storage systems, you will always think about a RAID controller. But it's important, RAID controllers are not supported because the RAID controllers, they build redundancy on the controller level, and the redundancy on the controller level will mask the physical disk. You have something like virtual disks, and this is not supported for storage spaces direct in Azure Stack HCI. So you always need direct access to your drives, and this can be provided via direct attached serial ATA drives, NVMe drives. For sure, we can use SAS host bus adapters for SAS drives. We can use host bus adapters for SATA drives. No RAID controllers. What's also important, as soon as you configure storage spaces direct on an Azure Stack HCI host, there can be no longer any fiber channel, ASHCI or fiber channel over Ethernet configurations. So you are even not allowed to start the ASHCI initiator on an Azure Stack HCI host. So no ASHCI connectivity, no fiber channel connectivity, even not for backup or things like this, only SMB traffic. When we're using host bus adapters, the cards must be implemented in simple pass-through modes. Some of these host bus adapters have additional logics, additional functionalities. The disks have to be simple pass-through to the operating system. So if we are thinking about servers, you know the tower servers, you know rack servers with the small 1/8 form factor or the 2 heights form factor. If you have limited drive capacity in your server, you can attach JBODs, so disk enclosures, to your server chassis. So the typical scenario is to have internal disks in the servers. This is what you will usually use and what I would recommend. In a typical 2 heights server, you will have 24 drive slots in the front, and you can put SSDs, NVMEs, hard disk drives in there. If you are running out of slot capacity, you can use JBODs, but please keep in mind there's no multipathing to the JBOD. This is a single connectivity here. Maybe this could be your single point of failure regarding this one server. In Azure Stack HCI, we know we always have minimum 2 servers where we have redundancy across the servers. But in this single server, we only have one connectivity to the JBOD. It's optional to do it. What's absolutely not supported to have this mesh configuration, we can see on the right-hand side. Why do we show this to you? When you think about Windows Server 2012 and Windows Server 2012 R2, then this part here and this configuration was supported as a scale-out file server cluster with external JBODs. In this scenario in Windows Server 2012 and 2012 R2, each JBOD had to be cabled to each server. And this whole cabling we see here is done in Windows Server 2016, 2019, 2022, and Azure Stack HCI via the software-defined storage bus. So we don't use any longer any cables between the servers except the network connectivity. And this is important to keep in mind because if you would build this, it would not be supported and it would not work. So always direct attached. So each server has its drives. So a server can have NVMEs only. This is a possible configuration. So each server has NVMEs only. It's possible, it's supported. It's very, very powerful to have this configuration. You can start with 4 NVMEs. This is minimum because in this scenario, all the NVMEs will be for capacity. Maybe a bit cheaper in the configuration is a SSD for capacity, where we use only SSD drives, and the SSD drives will provide the complete capacity as storage capacity. No data capacity, no storage capacity is used for cache. In the scenario where we use NVMEs and SSDs in combination, the NVMEs will be selected as cache drives and the SSDs will be selected as capacity drives. It's also possible to combine NVMEs and hard disks, and it's possible to combine SSDs and hard disk drives. Regarding Microsoft, it's also supported to have 3 storage tiers with NVMEs, SSDs, and hard disk drives, but I don't know any OEM certified, Azure Stack HCI certified solution that uses this 3-tier concept. From a technical perspective, it's possible and it's supported. So what we can see here are different configuration options. We cannot use configuration option 1 in server 1 and configuration option 2 in server 2 and configuration option 3 in server 3. So each server in our Azure Stack HCI configuration has to be from the type 1 or from type 2 or from type 3. So each server needs the same drive layout, the same number, the same types. So on the next slide, we can see the supported configurations. It's possible to have all persistent memory, all the same model, minimum 4 persistent memory modules in each server. More are always possible, but this is the minimum requirement. All NVMe, minimum is 4 NVMEs. All SSDs, also minimum 4 SSDs. If we use persistent memory and NVMe or SSD, we need 2 persistent memory modules. They are used for cache, minimum 4 NVMe or SSDs. It's possible to use NVMe SSD, in this case, 2 cache drives, 4 capacity drives. It's always 2 cache drives and 4 capacity drives minimum. It's also possible to have 3 cache drives and 6 capacity drives, or 4 cache drives and 8 capacity drives. It's possible to have 2 cache drives and 8 capacity drives. So the relation must always be suitable. So it depends on your throughput of the cache, which configuration makes sense. So if you look, for example, at the configuration 2 NVMEs and 4 hard disks, we could put 20 hard disks behind these 2 NVMEs, and the NVMEs would not be the limitation factor here. When we think about the SSDs in combination with hard disk, then when we have 2 SSDs for 20 hard disks, we are nearly on the same level. We will see this on the next slide when we compare the performance. So it must always be a suitable configuration regarding your needs and regarding the configuration of the different storage layers. So when we have a look at the different drive types, the question is, why do we combine these drive types? Let's have a look at the hard disk drive. A hard disk drive has a relatively good throughput when it comes to sequential workload. So this means we have a continuous data stream to this hard disk drive, write or read. We can have up to 300 megabytes per second. It's a very good throughput. If it comes to random I/O, we have 150 IOPS. This can be less than 1 megabyte per second if we have full random 4K block size. So this means hard disk drive is powerful for sequential workload. It's not so powerful for random workload. Let's compare it to a solid state drive. In solid state drive, we have a better throughput. Depending if it's serial ATA or SAS, we have 600 megabytes to 3 gigabytes throughputs. The interesting thing is we have 60,000 to 600,000 IOPS per second when it comes to random workload. So for sequential workload, a hard disk drive is 2 times up to 10 times faster. Sorry, a solid state drive is minimum 2 times, maximum 10 times faster than a hard disk drive. Sequential workload. Random workload, let's see, 150. It's not 1500, this would be 10. It's not 15,000, this would be 100. So it's 400 times faster in random I/O, a solid state drive. And if we have one of the fast types here with the 600,000 IOPS, it's 4,000 times faster than a hard disk drive. So let's imagine this, and this is the reason why Microsoft allows us to combine this. Let's imagine you have 2 solid state drives as a cache drive for the hard disk drives. Then we can take the advantage of the performance of the SSD drive and optimize the traffic to the hard disk drive, because the hard disk drive is on the second layer, the capacity layer, and the data is written there in a sequential workload. We will see this in one of the next slides. The non-volatile memory express NVMe drives have more throughput and more IOPS per second. It's amazing when you look at this here, what's the factor between hard disk drives and NVMe regarding the IOPS. Yes, these are the very fast NVMe's, but these are here also the fast hard disk drives. Yeah, so this is a huge difference here when we are looking at the random I/O. The persistent memory is on the same level regarding the throughput and the IOPS. But what's interesting for the persistent memory is that we have a reduced latency. For sure, the latency is the highest with the hard disk drives. So it takes time till the hard disk drive spins up before the read-write heads find the position. So we have something like about 10 milliseconds latency. For a solid state drive and for a NVMe, we have 0.1 milliseconds. It's already ultra fast because the persistent memory is equipped in a memory slot of the main board. We have shorter path to the CPU, and the persistent memory has something like 1 microseconds. So it's the fastest memory, the fastest storage we actually can get in this persistent memory modules for a storage spaces direct configuration with Azure Stack HCI. So the drives and the role of the drives is selected automatically. So it depends on which drives we combine, but usually when we combine hard disks and SSDs, the SSDs will automatically select it as cache drives. We can see this for the NVMe's, and we could add in our mind the persistent memory modules. I already mentioned the behavior of the cache, because if we are using hard disk drives, we have seen this huge difference in the random I/O. So a hard disk is fast in sequential write and read actions, but it's ultra slow for random I/O. This is the reason why writes are cached and reads are cached to use the random performance of the SSDs and combine these random transactions to SQL transactions for the hard disk layer. It's a really great algorithm. This algorithm also recognizes if we have a flash-only scenario with cache, because in the flash-only scenario with cache, we have the advantage that we can consume the drive writes per day from the NVMe to reduce the load on the SSDs. When we read data, we have the situation that reading data directly from an SSD nearly has no impact on the endurance. But if we would put everything into the cache and then read it from the cache again, this would be an additional load on the cache drives that would reduce their time, what would increase their drive writes per day. And this is the reason why in an all-flash scenario with cache, reads are not cached. When you want to have a look at this configuration, you can do this in the perfmon, because there will have additional counters for this cluster storage hybrid disks. What we have seen are hybrid disks, and these disks are visible in the perfmon, where we can get the counters to see the throughput. In this configuration, we have 4 capacity drives, and we have 2 cache drives. We have the cache drive 5 and 5, and the cache drive 6 and 6, and the capacity drives 0, 1, 2, and 3, and these are combined to these hybrid drives. The drive requirements we can see in this list here, where we can see the cache behavior in different configurations. All NVMe configurations. There we have capacity drives NVMe. We don't have a cache by default, but if we have different NVMe drive types, we could configure a manual cache. This is optional possible. This is not the default behavior. If we have all SSDs, it's the same. When we have NVMe's and SSDs, the NVMe's are the cache drives, the SSDs are the capacity drives. The cache is configured for write only, as we have seen in the previous slide. NVMe and hard disk, the NVMe's are for cache, the hard disks for capacity. The cache is configured for read and write. The same for SSD and hard disk in combination. SSD is cache, hard disk is capacity, cache behavior is read and write. If we have this 3-tier configuration, the NVMe's are for cache, SSDs are and hard disks are for capacity, and we have 3 storage layers where we have a mixed behavior. We have a read-write cache configuration for the combination of NVMe and hard disks, and we have write-only for the SSDs. When we talk about cache, many customers think, oh, cache, what happens if we have an outage? Then usually the data in the cache is lost. And it's the same situation in storage spaces direct. For sure, if we lose drives, the content we had of this on these drives is lost. But storage spaces direct has an algorithm, I already mentioned this, where we have a redundancy across the servers. This means, as we can see here in the Threeway Mirror, the data is written in 3 copies on 3 different drives on 3 different servers. This means that also the cache is redundant, as we can see here. It's written here, here, and here. And what's important to understand, storage spaces direct does not write the or copy the files or the hard disk. Everything we store in storage spaces direct volumes is stored in 256 megabyte blocks, and these blocks are called slabs or extents. So these slabs or extents are distributed across the servers to increase performance and to provide the redundancy we expect in our configuration and we require in our configuration. We will see more information about the redundancy later. In this 3-server scenario, we can have a 3-way mirror. In a 2-server scenario, we can have a 2-way mirror or nested resiliency. In a 4-server configuration, we can have a 3-way mirror or dual parity. What's important, we always have redundancy across the servers. So also the cache is redundant. So if we lose cache drives or complete servers, we do not lose any production data. We only lose slabs or extents where we always have copies of them. If we expand our capacity, we will add capacity drives. And if we have a configuration with cache drives, the cache drive binding is rebinded. So the cache drives are rebound to the new capacity drives. And here we can see we always need a multiple whole number of cache drives to capacity drives to ensure that we have a balanced configuration. It's not good to have on the left NVMe 3 capacity drives and on the right hand NVMe only 2 capacity drives. So if we start with 2 cache drives and 4 capacity drives, we always should add 2 drives or 4 drives or 6 drives in each server. If we start with 3 cache drives and 6 capacity drives, we always should add 3 additional capacity drives in each server. So it depends on your initial configuration how you will extend your configuration of the drives in Azure Stack HCI. So let's have a more detailed look at how Azure Stack HCI stores the data. What we see in this animation, Azure Stack HCI will build 256 megabyte slabs or extents in size when we create a new volume. As soon as we create a new volume with a fixed size, not if we have thin provisioning, but if we build the volume with a fixed size, these extents will be created, these slabs will be created. So if we have a 1 terabyte volume, we will have about 4,000 of these slabs or extents. These slabs or extents will be distributed across the servers, and when we have a look at a 2-way mirror, we'll have the situation that on the server where we have the original extent, we will never have the copy. As you can see here, the blue one is the original, the gray one is the copy, and we will have always a copy on a different drive on a different server. Important is to know what we see in this animation is not exactly supported as it's shown here, because we have 3 servers and we can see a 2-way mirror. This is not supported in production, so if you have 3 servers, you always will have a 3-way mirror. With 2 servers, you can have a 2-way mirror or a nested resiliency. But to show you how this mechanism works, I think this is the easiest way, and you can have a detailed look at this in docs.microsoft.com, as you can see in the URL at the bottom of the slide. The interesting thing is, when we use this extents, and the extents are built automatically by storage spaces direct in Azure Stack HCI, it's easy to add servers. Because if we add servers, these extents can be redistributed so that the capacity of this additional server is consumed, and we will have a rebalancing of original and copy slabs. The rebalancing starts automatically within 30 minutes after adding the drives. If you need an immediate rebalancing, you can start this via PowerShell with optimized storage pool and then the name of the pool and the rebalancing will start immediately. Let's have a look at the different redundancy options. In the two server node scenario, we can have the two-way mirror. The advantage of a two-way mirror is that we can lose one drive, we can lose two drives in one server, we can lose a complete server. The disadvantage of a two-way mirror is that if we have lost one server, we cannot have any additional failure in the remaining server. This means if you shut down one server for maintenance, you will not survive any additional drive failures in the remaining server. This is the reason why I would recommend to you to always use nested resiliency in a two-way configuration. In this nested resiliency, we have a data copy across the servers, and additionally, we have a local copy of each extent. So this means 2 copies of each extent locally and 2 on the other servers. So 4 copies for each extent. For sure, this means that you only have 25% usable capacity, or your footprint of your volume is 4 times the size of the volume itself. But your advantage is you can survive a server failure and an additional drive failure in the remaining server. So if server 1 is down for maintenance or unplanned situation, then you can lose an additional drive in server 2 without any impact on your data. So I would always recommend to use the highest available redundancy level. In the three-way configuration, so a 3-node configuration, we have the three-way mirror for redundancy. This means we have the 3 data copies we have seen before when I explained the cache. This means we have 33% usable capacity. A three-way mirror can safely tolerate at least 2 simultaneous independent failures at a time. But what's important to know, in this configuration, we see 12 capacity drives. In Storage Spaces Direct says to keep the storage pool online, where we have the volume stored, we need minimum 50% of the drives. If we lose 2 servers, we don't have any data loss, but if we lose two complete servers at the same time, then we will have a downtime in our configuration without any data loss. If we lose 2 servers at the same time and additional drives, then we will have a data loss, yes. But if we lose, for example, 1 server completely and 50% of the drives in another server, we only will have a reduced number of drives, but we have full service availability and no data loss. So important is, in a Storage Spaces Direct configuration, we always need the node majority. We always have to ensure that we have a majority of the votes in the cluster. Based on the dynamic quorum configuration, we can have an majority of the votes even with 1 remaining node. So each node in a cluster has a vote, and also the witness has a vote. And it's important to always have a secure majority set in the cluster. This is built dynamically. To keep the pool online, we need the majority of the disk drives. This means 50% plus 1 additional vote, and this vote is provided by the pool owner. This is 1 server in the cluster, and this server is held dynamically. And to ensure that we don't lose any data, it's important to not violate our redundancy configuration. This means in the 3-way copy, we cannot lose 1 drive in each server. This would not be possible because we only have 3 copies. I mentioned we don't copy hard disk drives, but if you lose one hard disk drive in each server at the same time, we will have on this drive some original, on these 3 drives, some original and copy 1 and copy 2. So this means 2 independent simultaneous failures are okay in the three-way mirror, not 3. In a 4-way configuration, and we have seen this previously, we can also have 5, 6, 7, 8 nodes, but with more nodes, we don't have an additional resiliency level here. With 4 servers, we have additionally the parity. The parity has the advantage that we have more storage efficiency. We have the same 3-way redundancy we have with the three-way mirror. The disadvantages of parity that the parity has to be calculated, so it has CPU impact. For sure, we can combine mirror and parity to have a so-called mirror accelerated parity volume to take the advantage of the performance of the mirror and the advantage of the parity for the storage efficiency. Important is to understand, if we have 4 servers, 5 servers, 6 servers, we can survive 2 simultaneous failures, 2 simultaneous independent failures. 2 servers can fail, 2 hard disk drives in 2 different servers can fail, but it's not okay to have 2 servers failed and an additional disk failure in an additional server. The only exception is if we have scope volumes, where we have volumes pinned to specific servers, where we have the situation that we configure the fault domains, not on the servers, but on the racks or on the side. And when we have stretched clusters, because in stretched clusters, we have an additional redundancy layer here. Yeah, when we look at the drive symmetry, we already discussed this. Then we have the clear statement that the servers should have the same type of drives. For example, if one server has NVMe, they all have to have NVMe's. They have to have the same number of drives in each server. But for sure, if one drive fails, it might be temporarily the situation that we have a different number of drives till the failed drive is replaced. The model of drive and firmware should be identical on the servers if it's possible. If it can't be, carefully select drives to ensure that it fits to your already existing drives. It's okay to mix similar drives if the previous model is not any longer available. It's also possible to have different capacity drive sizes across the servers, but this may result in stranded capacity. Let's have a look at a scenario. Let's imagine you have server 1, and this server 1 has capacity drives with 10 terabytes of capacity. Server 2 also. In server 3, a drive is replaced where we now have 15 terabyte capacity. Then we will have 5 terabytes of stranded capacity. So the new larger drive can be used, but not with this full size. For sure, it should be clear when you look at this picture here, because we don't have any space on server 2 and server 1 to build the redundancy to save the extents we need to build the redundancy. It might happen that you add additional drives, like in this scenario, not where you add additional drives, but where you will replace a drive with a larger model, where you expect stranded capacity, but where you will realize, oh, I can use the full capacity. Because in this scenario, we have the situation that the redundancy could be built with the remaining capacity on the rest of the servers. But it's very difficult to calculate this. So the recommendation is to use drives with identical size. If you have different drive capacities, then the recommendation is to plan with stranded capacity and not to plan with using this additional capacity. If we use cache drives with different capacity, maybe because the cache drive on the right-hand side was replaced and the initial model was not available any longer, then we have to know that the ratio of the cache changes, and the ratio is very important. I mentioned this, 10% of the capacity drives have to be provided as cache drive capacity, and this is always to be ensured. In this configuration, we will see a different throughput regarding if the extent is written to the right hand or to the left hand side in this configuration. So this might happen, but this is not recommended to design a solution based on this. So let's have a look at some untypical scenarios. So what's supported and what's possible? You should not design the solution based on this configuration, but it might happen because of some replacements. Let's imagine we have 3 servers, and server 1 has 2 NVMEs. Then it's clear each server needs 2 NVMEs. But what we can see here, the NVMEs are different. Server 1 and 2 has model X, and server 3 has model Z. So each server also has 10 SSDs, and the SSDs are identical. So we have the difference here in the cache drive. The number is the same, the type is the same, the size is, the limitation factor is provided by the server with the smallest cache drive size. This scenario might happen if we replace cache drives in server 3. You shouldn't design a solution if you implement it new from the scratch at the customer side. What's also possible that we, for example, have here cache drives in each server, 2 SSDs, and we have 10 hard disk drives in the servers, in each server, but a different mix. In first server, we have 7 from the one type, 3 from the other type. In the second server, we have 5 from each type. And in the last server, we have 1 from the first type and 9 from the second type. Might happen if you replace drives, might especially happen if your OEM provides replacement drives from the same category regarding performance, size, and throughput, but not from the same hard disk vendor. This might happen. It's also supported to, for example, have here NVMe cache drives. Here in each server, 2 times 800 gigabytes. Now we have hard disk drives, where in the third server we have larger drives. Maybe the 4 drives in server 3 failed one time, and we had to pull them out and replace them, but our replacement disks were larger. In this configuration, we will have stranded capacity in server 3 we cannot use here. It's also possible, for example, to have a configuration where we have different cache drive sizes. Let's imagine we had 4 times 1.2 terabyte SSD as cache in each server. And now we had to replace some cache drives in server 1 and server 2. But the initially used 1.2 terabyte cache drives were not any longer available, and we had to replace them by cache drives with 1.6 terabyte. This is not recommended. This is supported if it might happen. What's not supported is, for example, to have in one server 6 NVMEs and 18 hard disks, And in the other one, 6 SSDs and 18 hard disks. Yes, we have in both servers 6 cache drives and 18 hard disk drives, but we have different drive types for the SSDs. It's also not possible to say, okay, I have 2 servers with 2 cache drives and 10 hard disks, and I have 1 server with 4 cache drives and 20 hard disks. Even if the overall capacity is the same, we always have to have the same number and type of drives. Conclusion, this means same type of drives in each server is required. Same number of each type drive in every server is required. Same drive model, so size and so on model, is recommended. So, and it's clear if you replace drives, these two things, model, maybe also size, may vary if this initial drive is not provided by your OEM manufacturer as a replacement drive. Let's have a look at the Azure Stack HCI network requirement. All the data between the servers is distributed, all the slabs are distributed via SMB networking, and the networking should always be a high bandwidth, low latency network. This can be provided by minimum 10 gigabit per second network interfaces, always redundancy. You should have minimum 2 of them. The recommendation is to have faster connectivity, so 25 gigabits or more. Actually, we can get network adapters with up to 400 gigabytes port speed. And it's absolutely recommended to use RDMA. You can use Iwarp or you can use Rocky. So RDMA over Converged Ethernet. We can have a switched configuration or also switchless. We will have a detailed look at this in a few minutes. Let's talk a few seconds about RDMA. RDMA stands for Remote Direct Memory Access. The advantage of RDMA is that we bypass a part of the kernel stack and allow the network interface cards to communicate directly together to where we have an offloading of traffic from the CPU to the network interface card. This increases speed, this reduces latency, and this optimizes the full storage workload. There are 2 different implementations of RDMA. We can use Iwarp. Iwarp is actually recommended by Microsoft. Rocky and Rocky V2 were recommended in previous versions of Storage Spaces Direct. When we have a look at the technical situation, then both Rocky and Iwarp are RDMA technologies. RDMA ensures we have the offloading from the CPU to reduce the CPU load, to reduce the latency, to optimize the throughput. The difference is that Rocky is more complex in configuration than Iwarp, because Rocky, RDMA over Converged Ethernet, uses VLAN tags to provide storage classification to ensure that we have a lossless communication via the network. And this means if we are working with switches, not in a switchless scenario, but we are using with switches, the switches for Rocky need specific technical features to be compatible with this. The first requirement is 802.1q. It's the VLAN specification. I mentioned for Rocky, we need the VLAN tags to provide the traffic classification. We need the IAE 802.1QBB standard. It defines the priority flow control. we must prioritize our storage traffic in our Rocky configuration to ensure that we will not have any data package drops on the network for the storage traffic. The 802.1QAZ is the specification for enhanced transmission selection. And the IAE 802.1AB is the specification for the link layer discovery protocol. We need these 4 specifications on the switch to have a switch that supports Rocky. Microsoft has seen a lot of misconfigurations in Rocky, and this is the reason why Microsoft recommends to use Iwarp. You don't need to have control of the top of the rack switches. It doesn't matter if they have the requirements from the previous slides or not. Maybe we will not have access to the solution after we deploy it. Maybe we already used Iwarp. Maybe you are unsure which topology we should choose. These are all reasons why we should use Iwarp. For sure, we can also configure Iwarp with traffic classification, with a prioritization. So for Iwarp, we can have the same configuration we have for Rocky, but in Iwarp is optional. In Iwarp, it's optional to optimize the network traffic. In Rocky, it's required. So Rocky you should use if you are familiar with Rocky and if you are comfortable with managing the data center bridging network requirements. These data center bridging network requirements are optional for Iwarp. They are required for Rocky. So when we are thinking about the network interface cards, in Azure Stack HCI, it's possible to have dedicated physical network interface cards, but it's also possible to team the cards. We have a switch embedded teaming mechanism where we can build an Hyper-V switch with switch embedded teaming that combines the network interface cards, minimum 2, maximum 8 of them, to a set team where we have virtual adapters for the host and virtual adapters for the virtual machines. It's also possible to provide a configuration where we have a set switch for our Hyper-V virtual machines and where we have dedicated physical adapters for the SMB traffic, the storage traffic we mentioned in the previous slides. So you can work with full dedicated physical NICs, but you can also build the redundancy based on the teaming and provide the dedicated required network adapters on the logical layer. A very interesting option is to build an Azure Stack HCI switchless configuration. In the switchless configuration, we have the situation that the high performance storage network interface cards are directly connected to each other, where we don't need high performance switch ports that are usually more expensive than the slower switch ports. When we have a look at this configuration, then the red and the black marked NICs, they are both directly connected for the storage traffic. For sure, we need some additional network interface ports for our virtual machine traffic, because the virtual machines, they should be reachable from the network. So our green network interface card here and the blue one, they are connected to switches. But maybe we have the situation that the blue and the green network interface card, maybe these are 10 gigabit ports that are teamed, so we have 20 gigabit speed for the virtual machines, and 20 gigabit should be very affordable. And maybe the red and the black network interface port, these directly connected storage ports, maybe 100 gigabit ports because we have a full flash NVMe configuration. And if you have a look at the price difference at the switches between 10 gigabit port speed and 100 gigabit port speed, you will see a huge difference. So this can be an interesting scenario to have the storage traffic internally and the virtual machine traffic externally with less switch ports with less speed. A direct attached configuration is possible with 2 nodes, but it's also possible with 3 nodes. In this 3-node configuration, we need a full mesh configuration. So not a circle regarding the cables, but each host has to be connected to each other host. This is possible with dual port NICs in each servers. We can also build a switchless configuration with 4 servers. From the theoretical perspective, it would also be possible to build it with 5 servers, but as you can see here, we have many cables, so the advantage we see at 2 servers and 3 servers. This will be a disadvantage in 4, 5, 6, 7 server configurations because the cabling will get a small chaos there. When we combine what we have learned in this module about the hardware requirements, we can build an Azure Stack HCI solution on our own. So we can select the CPUs, the memory, the network interface cards, the host bus adapters, the drives based on what we have learned. Or the recommendation is to use a certified, validated partner solution. And this Azure Stack HCI certified systems can be found in the Azure Stack HCI catalog. Important is to know that the Azure Stack HCI certified systems in the Azure Stack HCI catalog are validated based on a standardized evaluation process provided by Microsoft. So it's not possible to design an Azure Stack HCI theoretical and bring it to the catalog without testing it. So every OEM that wants to provide a certified Azure Stack HCI solution has to build the solution on physical hardware and run the private cloud simulator provided by Microsoft with standardized testing scenarios. This private cloud simulator will put workload on the machines. The private cloud simulator will put faults on the machines, and the private cloud simulator will run several days. Usually the minimum runtime is 5 days, and if a system survives the private cloud simulator, the OEM can provide the result to Microsoft and bring the system to the Azure Stack HCI catalog here. So let's have a short look at the Azure Stack HCI catalog. When we open the website for the Azure Stack HCI catalog, we will see Microsoft.com HCI. This is the Azure Stack HCI landing page. And here we can click on Find an Azure Stack HCI partner. We can plan a solution. We will do this in a later module, or we can discover solutions. When we discover solutions, we can see we have solutions from different vendors, and we can see here there are integrated systems and validated nodes. Both the integrated systems and the validated nodes survived the private cloud simulator test. If they don't survive it, they are not listed here. Microsoft recommends to choose integrate systems. Why does Microsoft recommend to choose integrate systems? The integrated systems provide some additional value. There's no difference in performance, there's no difference in stability and so on. So the integrated system provide additionally the firmware and driver updates via Windows Admin Center. We will see this in a later module when we use update for the Azure Stack HCI configuration, the Windows Admin Center. Then the integrated systems can also provide these updates here. The integrated systems provide additional support from Microsoft and the OEMs. The integrated systems provide the additional testing for secured core server, but for sure also a not integrated system can be a secured configuration. If you are looking for reliable, performant, stable Azure Stack HCI configuration, you have this in both scenarios, integrated systems and validated nodes. For sure, you can filter for CPU, for GPU, for storage, for features, what you prefer. So maybe you prefer Intel or AMD, maybe you prefer specific GPUs. And for sure, you can also filter for your preferred partner. Let's filter here for one of these Azure Stack HCI solution partners. Then you will receive a list of the certified systems. Here you can see the systems from primeLine Solutions, where we have one configuration with Intel scalable CPUs and two different configurations with AMD, one with AMD 2nd Gen EPYC and one with AMD 3rd generation EPYC. So this catalog is your source when you need information about the available certified solution. If a system is not part of the Azure Stack HCI catalog, then it has not successfully passed the private cloud simulator, or the OEM has not uploaded the results to Microsoft, because if the OEM does it, the functionality or the system is provided in the Azure Stack HCI catalog.